To demonstrate the calculus of vector-valued functions, here is a vector-valued function. R of t is equal to t times e to the t, tangent squared of t, and the natural log of t divided by t. I'm interested in finding both the derivative as well as the indefinite integral of this function. Now, as far as derivatives are concerned, it's simply a matter of making sure that you are selecting the appropriate rule for derivatives and then applying it. In the first case, this would be a product of two functions. So we're going to take the first function times the derivative of the second function plus the second function times the derivative of the first function. In the second case, we have a composition of functions. So we're going to apply the chain rule coupled with the power rule. So the power rule says 2 times whatever that thing was to the first power, and then multiply by the derivative of whatever was on the inside function in this case being the tangent of t. And in our third case, we're going to see the quotient rule. Quotient rule is low, d high, less high, d low, over the square of what's b low. That's right, I just rhymed b low with d low. My next hit album comes out soon. Now, though it's not necessary, we could factor out any e to the t, do a little bit of work with this to pretty it up a little bit, and then 1 minus the natural log of t divided by t squared. No problem. Just straightforward Calc 1 problem applied 3 times, take 3 derivatives. Now, as far as antiderivatives are concerned, I'm going to recommend that you treat them one at a time rather than trying to do all 3 at once, because they're all going to use different techniques. For housekeeping purposes, we'll call these functions f of t, g of t, and h of t. So we'll start with the indefinite integral of f of t, dt. So the integral of t e to the t, dt. This one's going to be an integration by parts, since we have a product of an algebraic function with an exponential function. So we'll let u be equal to t, we'll let dv be equal to e to the t dt. We differentiate u, and we integrate dv. The integration by parts formula states that the integral will be u times v, so t e to the t, minus the integral of v times du. Reintegrating the e to the t does absolutely nothing. Now, as I mentioned in the last video, we'll also need a constant of integration. We'll refer to that as c1. For the second integral, mouth is full of cheese right now. Just had some string cheese. Delicious. We'll be integrating the tangent squared of t, dt. In order to integrate a tangent squared, we're going to make use of a trigonometric identity, specifically a Pythagorean identity. We're going to refer to the tangent squared as secant squared of t minus 1, both of which can be integrated directly. Secant squared of t will become tangent of t, and 1 will become t. So tangent of t minus t would be the antiderivative of tangent squared of t. We'll tag on that second constant for that. And finally, for h of t, we are integrating the natural log of t divided by t dt. There are 2 ways to do this one. One way would be integration by parts. The other one, which should be a little more straightforward, we're going to let u be equal to the natural log of t. Therefore, du is going to be 1 over t times dt. So we can split this up as natural log of t times 1 over t times dt. That way our integral simply becomes the integral of u du. Power rule states that that antiderivative will be 1/2 u squared plus a constant. So final answer for this one is going to be half of the natural log of t, quantity squared, plus that constant of integration. So our final answer for the integral of r of t dt involves putting all of these back together. So for our f of t, we got t e to the t minus e to the t. We'll group all of the constants together at the end. That's supposed to be a t there. For the g of t, we got tangent of t minus t. And for our third one, we got half of the natural log of t, quantity squared. And this will be plus the vector c1, c2, c3, referring to our constant of integration. So, hope this was informative and that everybody remembers all of their techniques for integration.